Okay, so I want you to imagine for a second that you're uh, a high-value target,
Okay.
a diplomat maybe,
Yeah.
or I don't know, a VIP witness. You've got bodyguards, of course.
Yeah.
But these aren't just guys in sunglasses standing by the door.
Right.
Imagine if every single time you walked into your safe house, the layout of that house completely changed.
Oh.
The hallway that was on the left is now on the right. The bedroom is in the basement. The windows have shifted 3 feet up the wall.
And just to make it more stressful, imagine the floor is covered in like invisible pressure plates. If you step on the wrong tile one that wasn't there 5 minutes ago, an alarm screams and the entire house just locks down.
It sounds like a paranoid fever dream, or maybe a scene from Inception. But as we were going through the research for today's deep dive, I realized this is literally, not figuratively, what's happening inside our computers.
It is thousands of times a second. Today, we are looking at the invisible bodyguards inside our operating systems.
And we're doing a technical breakdown, right?
Yeah.
The source is a document called Buffer Overflow Protections.
Yeah, it's basically a field guide to how modern systems stop hackers from hijacking your program.
And I think hijacking is the key word here. We aren't talking about preventing someone from guessing your password.
No.
We're talking about preventing someone from crashing your software, or worse, taking complete control of it by exploiting memory errors.
Exactly. This is the low-level warfare of binary exploitation. And looking at the source material, it's clear that the defense has had to get very, very creative.
Creative and complicated. I have to be honest, when I first opened this file Buffer Overflow Protections.md, it felt like I was drowning in alphabet soup.
I can see that.
ASLR, PIE, NX, DP, RLRO. I mean, it's a lot of acronyms for one sitting.
It definitely is. Security engineers love their acronyms, but the cool thing is each one of those represents a specific tactical evolution in a decades-long game of cat and mouse.
So that's our mission today. We're going to decode that soup. We need to figure out what these things actually do. Are they shields? Are they traps? And the big question that kept popping up in my head was, do they actually work? Or are they just slowing the inevitable down?
The short answer is they work, but they aren't magic. It's a system of, randomized layouts and strict do not enter signs. And while the source is based on lab notes, the concepts are actually pretty intuitive once you strip away the jargon.
So let's strip it away. Let's go back to that shifting room concept I started with. In the security world, this is the first line of defense, right?
Right. This is ASLR. Address space layout randomization.
ASLR. It sounds technical, but if I'm reading the notes correctly, this is essentially just a chaotic shuffling of the deck. But to appreciate it, I think we need to understand what life was like before ASLR.
That's a great point. In the good old days of computing, and I use that term very loosely, when you ran a program, it was incredibly predictable.
Predictable how? Like the layout was static.
Completely static. Every single time you opened an application, the operating system would load it into the exact same place in the computer's memory. The stack started at address A, the data was at address B, and the code was at address C. Every single time on every machine running that OS.
Which I assume was great for efficiency. The computer knew exactly where everything was supposed to go.
Great for efficiency, terrible for security. Because if I'm a hacker and I find a vulnerability, say a buffer overflow, I need to know where to jump to. I need a specific memory address to redirect the computer to my malicious code.
And if the address is the same on my machine as it is on yours, and the same today as it is tomorrow,
then I can write one exploit that works 100% of the time. I know exactly where the door is, and I can walk right through it. It made mass-scale worms so much easier to write.
Enter ASLR, so the kernel steps in and decides to spice things up.
Exactly. ASLR is a kernel-specific protection. Now, when you run a program, the kernel says, okay, we're going to load the stack and the libraries and the heap, but we aren't going to put them where you expect. It just picks random memory locations.
So if I'm the attacker and I try to jump to address X, thinking that's where the vulnerable function is,
You jump into empty space, or you hit a restricted area and the program crashes. Either way, you don't get your shell. The attack fails because the map has changed.
it's like trying to rob a bank, but when you get there, the vault has moved to a different city.
Yeah, that's a good way to put it.
Now, the notes mention that this randomization isn't just one big blob. The computer separates memory into different chunks, right? The
Yeah.
stack, the data, the code. Do they all move together?
Not necessarily, and that's a crucial distinction. On by86 architecture specifically, we see different behaviors for different segments. The stack is very easy to randomize.
Because the stack is just temporary scratch space, right?
Yeah.
It grows and shrinks as functions call each other.
Essentially, yeah. The addresses there are relative to pointers, like the stack pointer, so the OS can shift that starting point around without breaking anything. It's trivial math for the CPU.
What about the data segment, where global variables live?
That can be randomized too. But the tricky part, and the notes really emphasize this, is the code itself.
The actual instructions,
Yeah.
the text of the program.
Right. Historically, the executable code sat at a fixed address. So even if the stack was dancing around, the main body of the program, the house in our analogy, was still sitting on the same street corner.
So ASLR moves the furniture, but the building stays put.
In basic ASLR, yeah. Which leaves a loophole. If an attacker knows where the main function is, they might be able to leverage that even if they can't find the stack. They can use the code that's already there against you.
The notes actually dive into the Linux configuration here. It seems like you have some choice in how much chaos you want. It mentions 3 levels.
Yeah, Linux gives you a dial to turn in a file called randomize the VAS space. Option 0 is just disabled.
Living dangerously, no randomization at all.
I wouldn't recommend it. Then you have option 1. This is conservative randomization. It randomizes the stack, the libraries, and something called the VDSO.
Okay, but the notes seemed a little fuzzy on whether option 1 covers the data segment.
It kind of depends on the kernel version, but generally option 1 is most things, but not everything. It's trying to balance security with compatibility.
In option 2.
Option 2 is the full package. It's enabled, and that includes the data segment.
And the key takeaway here, which is pretty comforting for anyone listening, is that option 2 is the default for most modern systems.
Correct. Unless you go out of your way to turn it off, your computer is shuffling that deck every time you launch an app.
Oh wait, we just said the code segment might still be stuck in place. ASLR handles the stack and the libraries. But if the main program code is still fixed, doesn't that sort of defeat the purpose?
It doesn't defeat it, but it definitely weakens it. And that brings us to our next acronym. This one sounds delicious, but it's actually pure math. PIE.
PIE, Position Independent Executable.
Exactly. PIE is the solution to that fixed house problem. It allows the compiler to generate code that simply doesn't care where it lives in memory.
How does it do that? Doesn't the code need to know where things are to function? Like if I have a jump instruction, it needs an address.
It does, but instead of using absolute addressing like go to 123 Main Street, it uses relative addressing. It says, go to the house 3 doors down from where I am right now.
Ah, I see. So if the OS picks up the entire code segment and drops it in a completely different neighborhood, the instructions still work because they're just referencing things relative to themselves.
Precisely. This means the OS can now randomize the code segment base address, but PIE goes deeper. The notes mention it also randomizes the GOT and the PLT.
Okay, I flagged these in the notes because this is where the technical depth really ramps up.
Yeah.
GOT and PLT. Global Offset Table and Procedure Linkage Table. It sounds like bureaucracy.
It's necessary bureaucracy. Think of them as the program's dynamic address book.
Walk me through that.
Okay, so when your program needs to use a function from a shared library like printf, that function lives in libc.so, the standard C library.
And since we have ASLR, that library has been moved to a random location.
Right, so your program has no idea where print is. It can't just call it directly.
So it looks it up in the table.
Exactly. The PLT and GOT work together to resolve that address on the fly. The first time you call a function, the program basically asks the linker, hey, where's this function right now? The linker finds it, writes the address into the global offset table, and from then on, the program knows the way.
So the GIT is a list of phone numbers for all the external functions.
Yes. And if PIE is enabled, it ensures that even this address book, these tables, are at randomized locations. Because if those tables were in a predictable spot, an attacker could target them.
Right. If I know where the phone book is, I can change the number for pizza place to Hitman. You think you're ordering dinner, but you're actually calling trouble.
That is a terrifyingly accurate analogy. So PIE effectively randomizes all the signposts and the address books. No static targets left.
It sounds strictly better. Why would anyone ever turn it off? The notes mention a no pi flag.
Mostly for debugging or education. If you're learning how to write an exploit or you're trying to diagnose a weird crash, having addresses that change every single time makes your life miserable.
Right. You want the variable to hold still so you can see what's breaking. But in production.
In production, PIE should always be on.
Okay, so we've got ASLR and PIE. The room is shifting. The address book is rewritten. But let's play devil's advocate.
Always.
What if the attacker gets lucky? Or what if they find a way to leak an address? The source material makes a specific point that ASLR makes attacks difficult, not impossible.
That is the what if that keeps security engineers up at night. ASLR is probabilistic. If you can try enough times brute force, or if you can trick the program into revealing a memory address, you can de-randomize the layout.
So you figure out the secret offset and suddenly you know where everything is again.
Exactly. So we need another layer. We need a way to stop the attack even if they know where to go.
Which brings us to NX, or DEP.
The do not enter sign.
Yes.
Ideally. NX stands for no execute. In the Windows world, you'll hear it called Deep Data Execution Prevention. I actually prefer the Windows name. It explains the concept better.
Data execution prevention. It prevents data from being executed as code. But why was that even allowed in the first place?
Because of how CPUs are built.
Yeah.
To a CPU, bytes are just bytes. Historically, the computer didn't care if a piece of memory was supposed to be a picture, a text file, or a program. If the instruction pointer pointed to it, the CPU would try to run it.
Which is exactly how buffer overflow attacks work. The attacker injects their own malicious code, their shell code, into a data area like the stack.
Right. They pack the stack with code, overwrite the return pointer to point to the stack, and the CPU jumps there and just starts executing the data as if it were valid instructions.
So NX allows the operating system to mark pages of memory with specific permissions.
Exactly. It uses a feature in modern CPUs to say, this is the stack. It is for reading and writing data. It is not for running programs. It literally flips a hardware bit.
So if the attacker manages to redirect the flow to the stack, the CPU looks at that bit and says,
nope. It triggers a hardware exception. The program crashes immediately, but the malicious code never runs.
It's like trying to swipe a key card for a door you don't have access to. The door just doesn't open.
And you can actually verify this yourself. The notes mention a tool called readelf. If you run readelf del L on a binary, you can see these permissions.
What are we looking for in that output?
You're looking for a line that says GNU stack. You check the flags. If it says RW, that means read and write. That's safe.
But if you see RWE,
read, write, and executable, that is a massive red flag. That means the safety rail is gone.
the notes mention that modern compilers are smart enough to default to safety. You actually have to go out of your way to make a program insecure.
Yes, you have to use the del sec exec stack switch. You're effectively telling the compiler, I know what I'm doing, take the safety rails off.
Which you might do in a lab, but never in a real app.
Never. There are almost zero legitimate reasons to have an executable stack in modern software.
Okay, so we've moved the target with ASLR and PIE. We've locked the doors with NX. But what if the attacker is trying to trash the place? Or what if they use a technique like ROP, return-oriented programming?
Ugh. ROP is nasty because it uses the existing valid code already in memory to do bad things. NX can't stop that because the code is executable.
So is there a way to detect that an overflow is happening before the attacker takes control?
That is where we get into the realm of traps. And my favorite term in this whole document, stack canaries.
I love this one. It's literally named after the coal mine tradition.
It is. Miners carried canaries because the birds were sensitive to toxic gases.
Yeah.
If the canary stopped singing or died, the miners knew to get out.
A bit morbid, but effective. So how does a digital canary work?
Well, it's actually embedded inside the function itself. It's a tripwire. The compiler places a secret, random integer value on the stack right between your local variables and the return address.
Okay, let's visualize the stack like a tunnel. You've got your variables, then this canary bird, the random number, and then the exit, the return address.
Correct. Now remember how a buffer overflow works? You write data linearly. You fill up the buffer, you keep writing, and you overflow towards the return address.
But to get to the return address, you have to write over the canary first.
You have no choice. You overwrite the canary with your garbage data.
And the program notices.
Before the function returns, before it uses that return address, it runs a quick check. It looks at that canary value on the stack and compares it to the original secret value it stored somewhere else.
And if they don't match?
If the values are different, the canary is dead. The program knows the stack has been corrupted.
And it pulls the emergency brake.
Immediately. It aborts execution. It usually prints something like stack smashing detected and just kills the process.
That is so clever. It stops the attacker from successfully redirecting control flow because the program commits suicide before the redirection can happen.
Exactly. It sacrifices the process to save the system. And again, this is usually on by default. To turn it off, you have to use the flag no stack protector.
Stack protector. It sounds so knightly.
It is a very effective defense. But like everything else, it has weaknesses. If you can read the stack using a format string vulnerability, for example, you can leak the canary value.
We'll fake the canary.
You fake the canary, but that requires an info leak first. It raises the bar significantly.
Speaking of raising the bar, the notes mention a few hardening techniques.
Yes.
Specifically, RLRO.
Yes, REL-RO stands for relocation read only.
And the notes distinguish between partial and full. What's the difference?
It comes down to timing.
Yeah.
Remember we said the program writes to the global offset table as it finds functions? That's called lazy binding.
Right.
Partial RRO leaves the gotchably writable, so that can happen. But if it's writable, an attacker can theoretically write to it too. It's a classic attack overwriting a GOT entry to hijack a function call.
So full RLRO fixes this.
Full RLRO tells the linker to resolve all those addresses at the very beginning, right when the program starts.
Do all the lookups now.
Exactly. And once they're resolved, it marks that entire section of memory as read-only. It freezes the address book.
So even if I have an overflow, I can't change the phone numbers.
Precisely. It hardens the binary against that specific type of redirection.
The notes also mention fortify. Is that like building a wall?
In a way, fortify source is a macro the compiler uses. It tries to be intelligent. If it sees you using a risky function like strandcopy.
Strandcopy is the one that just copies strings until it hits a null byte, regardless of buffer size, right?
Yeah.
The classic overflow culprit.
Right. If the compiler can figure out the size of the buffer at compile time, it silently replaces strappy with a safer version that checks the bounds.
So it's the compiler looking over your shoulder and saying, hey, you're about to pour a gallon of water into a pint glass. Let me stop you before you spill.
Or rather, let me add a check to make sure you don't pour more than a pint. But it can't catch everything, especially if the sizes are dynamic.
So we've got this incredible defense-in-depth strategy. But how do we actually see these in the wild? How do I know if my programs have these bodyguards?
The notes highlight a very useful toolkit for this. The main tool is checksec.
Checksec. That's exactly what it says on the tin.
It's a script, often integrated into GDB plugins like PETA. You run it on an ELF file, the standard executable format for Linux, and it prints out a nice table.
Like a report card.
A security stat sheet. It says canary found, yes. NX enabled, yes. PIE, yes. It usually color codes it too. Green is good, red is bad.
It makes the invisible visible. That's really cool.
It does, and for deeper analysis, there's ptrace. This is a system call that debuggers use to step through code and see how these protections are behaving in real time.
But there's a massive warning in the notes here that I think we need to broadcast loud and clear. It's about a command called alad.
Yes, this is a critical safety tip. alad is a standard command used to print the shared libraries required by a program.
Which sounds harmless. What libraries do you need? It's just reading a list, right?
It sounds harmless. But the way alad works in some versions is that it can actually execute code inside the file just to figure out the dependencies.
Wait, pause. So if I download a suspicious file from the internet malware, and I run all on it just to see what it is,
you might inadvertently run the malware. You're asking the malware, what do you need to run? And the malware says, let me start running and I'll show you.
that is a pretty major design flaw. Or at least a massive booby trap.
It is. The source explicitly warns, never run alt on an untrusted ELF file.
So what's the alternative? How do we check dependencies safely?
Use objump. It reads the file's header statically. It looks at the blueprint. It doesn't try to build the house. It's much safer.
Pro tip, use objump, not old, on anything sketchy.
Always.
So bringing this all together, we've decoded the alphabet soup. We've got ASLR and PIE shuffling memory around. We've got NX locking down the stack. We've got canaries as tripwires. And RELRO freezing the address books.
It's a comprehensive defense-in-depth strategy. No single layer is perfect. ASLR relies on probability. Canaries can be leaked. NX can be bypassed with ROP chains.
But the point is, each layer forces the attacker to work exponentially harder. It turns a simple smash and grab into a complex Ocean's 11 style heist.
That is the goal. Security isn't about making things impossible. It's about making them so expensive and difficult that the attacker moves on to an easier target.
So what does this all mean for the listener? Why should they care about stack flags and memory addresses?
It means that the software you use every day is fighting a constant silent battle. These protections are the unsung heroes. And for anyone interested in tech, learning to use tools like checksec is the first step in seeing that invisible war. It changes how you look at software.
It really does. It's not just code, it's a fortress with shifting walls and hidden traps.
A fortress that is constantly being tested.
And on that note, we're going to wrap up this deep dive into buffer overflow protections.
But before we go, I want to leave you with one thought from the source material that really stuck with me.
What's that?
The notes on ASLR explicitly state that it makes attacks difficult, not impossible. Think about that. We have randomized the entire universe of the program's memory. We have millions, billions of possible addresses, and yet an attacker can still find that one needle in the haystack.
It's a game of probability.
It is, if the math says it's random, but reality says it's still hackable. What does that imply about the limits of defense? Is it possible that in the digital world, nothing can ever be truly random enough to be safe?
Something to mull over the next time your computer installs a security update. Thanks for listening, everyone.
Stay curious and stay safe.